Right, so last time we were looking at the connection between linear functionals and their kernels and codimension 1 subspaces. Codimension 1 subspaces being the kernels of the non-trivial linear functionals. And then there was a dichotomy that these codimension 1 subspaces, these kernels, were either closed or else they were dense. And they were closed if and only if the linear functional was continuous, and they were dense if and only if the linear functional was discontinuous. And then I asked you to look at this exercise, which is also on a question sheet. The existence of discontinuous linear functionals, which you get from Hamel bases. Basically, you define it, first of all, on some countable dimensional subspace. Make sure it's discontinuous there. And then you define it however you like on the rest of the Hamel basis. And it's not going to get any less discontinuous than it was before. And then I said use C00 in order to get an explicit example of a discontinuous linear functional. In a way, you're almost cheating there and almost using Hamel bases. If you really want the Hamel bases to become sort of invisible, you should think of C00 as polynomials. So perhaps use polynomial functions, again with some suitable norm. As we know, the polynomial functions, or the polynomials, or C00, there's not a great deal of difference. So there's quite a lot of flexibility around as to the way you look at it. And then you've got various different ways you can think about trying to define a linear functional on those. And one way you can define a linear functional on polynomials is to evaluate at a point. If you arrange that the particular point you evaluate at to be sort of not involved in the definition of the norm, then it's quite easy to arrange for this evaluation to be discontinuous linear functional on the polynomials. But I'll let you have some fun thinking about that. Now, before we move on, let me just remind those listening that there was a handout today on measure theory. And this is essential background material, and it's examinable. It's examinable reading material. So you have to read this before the last Tuesday of term. That's before the Tuesday of week 10 of teaching. And we'll have a Q&A discussion on that material in the final lecture on that Tuesday. So I hope you'll come up with lots of questions for me. Right, so now our task now is to find the dual spaces of some specific examples. What does this mean? It means we're going to actually find lots of examples of continuous linear functionals, and we're going to prove that they're the only continuous linear functionals on certain spaces. Now, I say the proof of the first proposition is an exercise, but some parts of this exercise are actually quite tricky and may be best left till we've actually discussed the Hahn-Banach theorem. So the last part can be deduced from the Hahn-Banach. That's a finite dimensional deduced from Hahn-Banach theorem. Though it's a finite dimensional version of the Hahn-Banach theorem. And Hahn-Banach we're discussing in the next section. So you might want to postpone the very last bit. So what does this say? This is if you're in a finite dimensional norm space. Well, on a finite dimensional norm space, every linear function is continuous. So this E star equals E cross. Remember, E star, that's the continuous linear functionals. E cross is the linear functionals. Now, we know that all norms on finite dimensional spaces are equivalent. So in particular, you can, when you're trying to check whether a linear functional is continuous, you may as well assume you've got some standard norm like Euclidean norm when you're trying, and then it's pretty obvious then that linear functionals are continuous because linear functionals on a finite dimensional space are just given by multiplication by some finite matrix, essentially. Linear maps between finite dimensional spaces are just given by matrices, and in this particular case it's like just dot product with some particular vector is what's going on, and that's obviously going to be continuous in the usual setting, and since all norms on finite dimensional vector spaces are equivalent, so that's going to be continuous. So that explains why every continuous linear functional, which is E star, is every linear functional, which is E cross, has to be continuous. So that gives you E star equals E cross. Now, when you're dealing with finite dimensional vector spaces, as I say, the linear functionals are just like dot products with some particular vector, and so you end up with the dimension of your dual space being the same as the dimension of the original. This only goes for finite dimensional spaces. And then you can come back to E double dual and E. So what's this? This is the bidual. And there's a nice map from E into the bidual called the natural embedding. Whose properties we'll have a look at later. It takes X to something called X hat. So this is where X is in E. So for X in E and phi in E star, so phi is a continuous linear functional defined on E. So we've got phi of X is a nice scalar. Well, we define X hat of your functional to be phi of X. This means that X hat is a linear functional on the set of linear functionals. So X hat is a function defined on E star, taking values in F. And it's easily seen to be a linear functional. And it's easily seen to be a continuous linear functional because actually its norm turns out to be exactly the same as the norm of X, so less than or equal is obvious. When we come back in the next section, we'll see that this is an isometric linear embedding of E into E double dual. But in the case of this works for all norm spaces, but for finite dimensional spaces, because the dimension of E and the dimension of E star and the dimension of E double star are all the same, this isometric embedding actually has to be surjective as well, which is something you don't usually expect to happen for a norm space. In the infinite dimensional setting, it's a special case when you actually get this map being onto, whereas in finite dimensional setting, when you take the dual, you get the same dimension. Then you take the dual again, and you get the same dimension again. And the E is isometrically isomorphic to E double star or E star star, the double dual or the bidual. As I said, the bit about the isometric isomorphism there is the least obvious bit, and you can get that from the finite dimensional version of the Hahn-Banach theorem, which we'll be discussing some of in the next section. So that's finite dimensional spaces, but now let's have a look at our sequence spaces. Now, what do we mean by equality? Equality here is going to mean isometric isomorphism, but also in a reasonably natural way again. We'll see how there's a very natural way, if you've got an element of little L1, to use it to make a continuous linear function on C0. And we'll see that the linear function you get has got the correct norm, the norm of the associated little L1 element. And we'll see that this is an isometric linear isomorphism, and that you get all continuous linear functions on C0 that way. So this statement should be interpreted as saying, we will explain how to use elements of little L1 to give you linear functionals on C0, and this is an isometric copy of little L1, and you get every continuous linear functional on C0 that way. Then you do the same thing for L1 star being L infinity, but that's on the question sheet. So that's on question sheet 4. So we're going to do the first one in full. The second one's on question sheet 4. And I'll say a bit about the third one, but won't do it in full detail. But this is actually a Hilbert space result. Hold on, that's... So we'll discuss this rather briefly. Along with some more general stuff about the other LP spaces. But what we'll do is we'll do a full proof of this one here. So the proof that C0 star is equal to L1 which along the way you'll see what we mean by that. So we will show that there is an isometric linear isomorphism from L1 onto C0 star. Well, the onto is automatic because it's an isomorphism. So I could have said 2. Because it's an isomorphism, it has to be bijective, right? I didn't have to say onto. But we will have to prove onto in the proof. That's L1, that's C0 which is a bit difficult to tell my curly C's from my curly L's if you're not careful. That looks a bit better. Maybe it shouldn't be a curly C. Let's make it a straighter C. That'll make it easier. Right, so how do we do this? Let's start by fixing y in little l1, and we'll fix this temporarily. And say y is yn, n goes from 1 up to infinity. That's your sequence, okay? So you're in little l1, you must be a sequence. And of course we know that the sum from n equals 1 to infinity of mod yn, which is norm y, is finite. That's the one norm of y. Okay? That's what we've got to start with. Now, we're fixing y for the moment. Now, for x equals xn in C0, we have norm x infinity equals the sup over natural numbers of mod xn is finite. That's the norm on C0. Convergent sequences are bounded. In particular, null sequences are bounded. So we define phi y of x to be equal to the sum from n equals 1 to infinity of xn yn. Now let's just check this makes sense. This is the sum of complex numbers or real numbers, elements of f. We don't know whether it's real or complex. It doesn't matter. The same proof works for both. To see this makes sense, we just check absolute convergence. This makes sense because sum from n equals 1 to infinity of modulus of xn yn is smaller or equal to the sum from n equals 1 to infinity of, you can just replace xn with norm x infinity mod yn. Each of the modulus of the xn's is less than or equal to the norm of x infinity. And that's equal to norm x infinity norm y1, which is finite. So the series for phi y is absolutely convergent and convergent. Moreover, that also proves a bound on how big mod phi y of x is. Mod phi y of x is at most, the modulus of a sum is less than or equal to the sum of the modulus. So we get this estimate. It could be strict. But the modulus of a sum is less than or equal to the sum of the modulus. And that we already know is less than or equal to norm x infinity norm y1, which I'm going to turn around in a minute. Now, this shows that we now have a well-defined function, phi y, defined taking C0 into the scalars. Thus, we have defined a map phi y. I sometimes say phi, I sometimes say phi. Phi is the English pronunciation and phi is American and Greek. And that therefore is probably better. Phi or phi y defined on little c0 taking values in f. So at the moment y is still fixed and I want to look at the properties of this map phi y. Well, so again, remember phi y of x is the sum, I'll just remind you, sum from n equals 1 to infinity of xn yn with x equals xn as above. Y is still fixed at the moment. That's just a function so far, but it's not hard to prove that it's actually a linear functional. You just have to do a few routine checks. So routine checks show that phi y is linear. So phi y is in C0 cross. But we also have this estimate on how big it is. And I'll just turn this around, norm y1 times norm x infinity for all x in C0. So suppose you've got a linear map into the scalars with this property. What can you tell me about, is it continuous, and what can you tell me about its operator norm? Remembering that modulus is the norm on the scalars. So this says the norm of phi y of x, regarding modulus as norm, the norm of phi y of x is at most the one norm of y times the suit norm of x. Y is fixed at the moment. We're letting x vary through C0. So what does this tell me? What does this tell us about this linear map phi y? Is it bounded? If so, what can you say about its operator norm? It is bounded. So phi y is bounded. So I can say phi y is in C0 star. And then you've got an estimate on the operator norm, which is what? The one norm of y, yeah, that's right. You see, we've shown that the norm of the image is less than or equal to a constant. Remember, y is fixed at the moment. The norm of the image is less than or equal to a constant times the norm of the original. X is the thing that's being acted on here. The constant involved is the one norm of y, which is being fixed at the moment. So what we've done is we've shown for each y, we've picked out a bounded linear functional phi y whose operator norm is no more than the norm of y. What do we still have left to do to conclude the result that I'm claiming? We're close, we're nearly there, but we've still got some fiddly bits to do to finish. That's right. So we have to prove that every bounded linear functional has this form. So we've got to show that they all have the form phi y. We should also check that the map that takes y to phi y is linear. That's another routine check. So I'll add that in just as the next stage. Further routine checks. The map that takes y to phi y is a linear map from L1 to C0 star. That's not the same linear we just checked above. Above, we said for a particular y, phi y was a linear functional. Now we're saying that the map that takes y to phi y is a linear map from little L1 to C0 star. So different domains here. Phi y had domain C0, and this map has got domain little L1. So different domains, they're different maps. But it's still a routine check to check linearity, and it's almost identical to the previous check. It's just about rearranging infinite series of a sum of two things and things like that. So let's take that as read. So you now have a map, and the above shows that this linear operator has operator norm at most 1. But what we really want is that it should be an isometric isomorphism. So as you said, it should be onto. So it should be onto, and then we've got that the operator norm of phi y is less equal to the norm of y. So what else are we going to need? If we want it to be an isometric linear isomorphism. So let's say we want this to be yes, we need equality, okay? So we've got to do a bit of work to get the bound from below. So we want this to be an isometric linear isomorphism. So we'll show we're going to show that norm phi y op is greater or equal to norm y1, hence equality, because we got the other way round, and that every continuous linear function on C0 is one of these. So for all psi in C0 star, there exists a y in little l1 with phi y equals psi. Okay, so that's what we're going to do to finish. This isn't the shortest proof. There is a slightly shorter, more economical proof that gets you everything, but it's dangerous, and so I'm not going to give it. There's a subtle and dangerous mistake one can make when one tries to do this the quick way. Okay, so let's try to finish this off. Now, so first of all, we want to check that the norm phi y is at least as big as the norm of y. Of course, if y is a 0 element, this is particularly easy. But here is the strategy for dealing with it generally. So again, let y equals yn in L1 as above. So yn is, each yn is in F. So choose choose scalars alpha n in F with modulus of alpha n equals 1, so that alpha n yn equals mod yn. How do you do that? The usual way to do this, so we can take alpha n to be 1 if yn equals 0. Don't care what you do really if yn equals 0. And ifyn's not 0, you take it to be modulus of yn over yn. In either case, alpha n is a real or complex number with modulus 1, and alpha n times yn is mod yn. Now, look at alpha 1, alpha 2, up to alpha n, but then lots of zeros, which is in C0, which is a subset. It's in C00, which is, of course, a subset of C0. And let's call that X upper n. And maybe I shouldn't be using n. Well, it'll do. This is for each natural number n. So, what is the suit norm of this finite sequence? Yeah. Okay, that's good. And what's phi y of it? Well, you should sum from k equals 1 to infinity xnk yk, where those are the kth terms. But of course, that's really a finite sum. It's a sum from k equals 1 to n of alpha k yk. And what's that? That's a sum from k equals 1 to n. How do we choose the alpha k's? So that alpha k yk was equal to somewhere further up. Let's have a look. Alpha n yn is mod yn. So alpha k yk, having swapped my notation around a bit, that's mod yk. What do I conclude from that? I've got, for each n, I've got an element in C0 whose norm is 1, and the image is this non-negative real number. The conclusion is that the operator norm is greater or equal to this finite sum. So the operator norm of phi y is greater or equal to the sum from k equals 1 to n of mod yk. But that was true whichever natural number n you did. So now you can let n tend to infinity. Then norm phi y op is greater or equal to norm y1. So we get equality as required. Okay, we're going to have to stop there. So next time we'll finish this off by proving that every continuous linear function on C0 has this form.